Imagine a traveler from another sun, forged in a furnace we will never see, wandering for millions of years in the dark until it found us. For a brief heartbeat of cosmic time, it blazed across our sky, defiant, mysterious, and impossibly alive. But what did it leave behind, and what secrets still echo in its wake? As you listen, imagine the immense darkness between the stars suddenly broken by a tiny speck of ice and rock hurtling through interstellar space. This object has been traveling for millions, perhaps billions of years, crossing cold voids where light from any sun is a faint glimmer. It is an interstellar wanderer named 3I Atlas, and it is entering our cosmic neighborhood at breathtaking speed. At more than 137,000 miles per hour, about 61 kilometers per second, it plunges toward the inner solar system, racing through the darkness as if on an urgent mission. Almost nothing in our daily experience prepares us for the sheer velocity of such an object. In 1 second, it travels farther than many people drive in a day. Yet the numbers alone cannot capture the feeling of witnessing something so ancient and alien crossing the familiar orbits of our own planets. For centuries, astronomers have watched comets and asteroids bound to the sun's gravity, but they always trace looping paths that bring them back again and again. By contrast, 3I Atlas is on a hyperbolic trajectory, an open-ended path that will carry it through our solar system once, never to return. This simple geometric fact makes it an emissary from another star system and imbues its journey with a sense of urgency. We will have only a brief window to study it before it vanishes into the blackness between the stars. The question that animates this story is both practical and poetic. Will this interstellar visitor survive the perils of our solar system? Will it thread the main asteroid belt between Mars and Jupiter unscathed? Or might it fragment before we can learn its secrets? In exploring that question, we also explore our own curiosity. We are watching the sky not simply to protect ourselves, but to satisfy a deep human urge to understand objects that come from places we may never visit. Our first task in this narrative is to appreciate just how rare an encounter like this is. Before 2017, no one had ever seen an interstellar object pass through our solar system. Then came one Oumuamua, a mysterious cigar-shaped or pancake-shaped body discovered by the Pan-STARRS survey in Hawaii. It captured imagination worldwide because of its unusual shape, its tumbling motion, and its surprising acceleration as it exited the solar system. In 2019, 2I Borisov appeared, clearly identifiable as an interstellar comet because it displayed a bright coma and tail. It looked more like comets we know, but it was also moving too fast to be gravitationally bound to the sun. These two sightings mark the beginning of a new era of observational astronomy. For decades, scientists had speculated that pieces of other planetary systems drift through our own, but until Oumuamua and Borisov, that was just theory. Now we have confirmed not one, but two examples, each offering a treasure trove of data. When 3I Atlas was discovered on July 1st, 2025, astronomers recognized it as only the third interstellar object ever observed, and the first since Borisov 6 years earlier. Its name encodes its identity. 3 for the third interstellar object, I for interstellar, and 3I Atlas after the survey that first detected it. Unlike the near-Earth asteroids and comets that are named after mythological figures, this name situates the object squarely in the new field of interstellar debris. Each detection is like a message from beyond our planetary system, and because there are only 3 so far, Each one is precious. The rarity alone makes 3I Atlas worth detailed study, but so does its status as a comet, a body that, unlike Oumuamua, carries volatile ices that can reveal the chemistry of its parent system. Scientists hope that by analyzing the gas and dust 3I Atlas emits, they can infer details about the protoplanetary disk it came from and compare that with our own early solar system. The story of how 3I Atlas was found is almost as remarkable as the object itself. The 3I Atlas, Asteroid Terrestrial Impact Last Alert System, survey consists of telescopes located in Hawaii, Chile, and South Africa that scan the night sky to detect small objects that might hit Earth. On the evening of June 14, 2025, one of these telescopes captured images of a faint, slowly moving point of light. At first, it was just a tiny smudge among thousands of stars. Over the next 2 weeks, the telescope continued to photograph that patch of sky, but the significance of the data went unnoticed. On July 1st, Larry Deno, an astronomer at the University of Hawaii, ran the images through software designed to search for moving objects. He immediately saw that this faint object had an unusual trajectory. Follow-up observations by other surveys, including the Zwicky Transient Facility in California, quickly confirmed that the object's orbit was hyperbolic. In other words, its trajectory was not a closed ellipse, but an open curve. 3I Atlas was moving so fast that the sun's gravity could not capture it. It was from interstellar space. Pre-discovery images were soon found in archived data going back to June 14th. These additional points enabled scientists to refine the orbit precisely. As the news spread through the astronomical community, observers scrambled to secure time on larger telescopes. Every minute counted. Because 3I Atlas was already just inside Jupiter's orbit at discovery, it was moving swiftly toward the inner solar system, and the window for easy observation from Earth would be short. Astronomers at universities, observatories, and space agencies set aside competing projects to gather as much data as they could. The early days after the Yazi detection were marked by a sense of camaraderie and urgency. People who had studied Oumuamua and Borisov in previous years were back on phone calls and video conferences, planning observation campaigns. Science thrives on collaboration, and interstellar objects naturally inspire it, because no single telescope or team can gather everything. Coma morphology, light curves, spectral signatures. There was a lot to measure in a short time. For space enthusiasts, the search for data about 3I Atlas felt like reading a detective novel where clues appear in real time and the ending is uncertain. The physical characteristics of 3I Atlas were one of the first things observers wanted to know. Was it big like a mountain or tiny like a boulder? The answer would determine how bright it might become and how long it might survive near the sun. Early estimates based on its brightness spanned a wide range. Some initial reports speculated that it could be up to 20 kilometers across, much larger than typical comets. That would make it enormous compared with Oumuamua and Borisov. Yet as more data rolled in, including images from the Hubble Space Telescope, scientists revised those estimates downward. On August 20th, 2025, NASA reported that the object's diameter was not less than about 440 meters, but not more than 5.6 kilometers. That range still leaves significant uncertainty, but it narrows the possibilities. Even at the upper end, 5.6 kilometers is a respectable size for a comet, though it is not unusual by solar system standards. By comparison, 2I Borisov was about 1 kilometer across, and Oumuamua was roughly 200 by 35 meters in a cigar-like or pancake-like shape. The large size of 3I Atlas, if confirmed at the high end, could mean it contains a significant amount of pristine material. But size alone does not determine survivability. Many comets have disintegrated near the Sun despite being several kilometers in diameter because their internal structure was weak. The speed of 3I Atlas is also extraordinary. At discovery, it was moving at about 137,000 miles per hour relative to the Sun. As it falls toward the Sun, gravity will speed it up even more. That velocity means that any collision with even a small object could be catastrophic. But it also means that the time spent in the main asteroid belt, a region between 2.2 and 3.2 astronomical units from the Sun, will be short. The comet will cross that region in a matter of months. Scientists have to weigh these factors when considering the risks it faces. A key part of the narrative is the trajectory of 3I Atlas through our solar system. After passing inside Jupiter's orbit, it moved toward the inner planets. The orbit calculations show that it will reach its closest point to the Sun, or perihelion, around October 30th, 2025. At perihelion, the comet will be about 1.4 astronomical units from the Sun, roughly 130 million miles, or 210 million kilometers. That distance puts it just inside the orbit of Mars. Contrary to some sensational headlines that have circulated on social media, 3I Atlas poses no danger to Earth. The calculations show that it will never come closer than about 1.8 astronomical units, around 170 million miles, or 270 million kilometers, from our planet. For perspective, that means it will remain more than 400 times farther away from us than the Moon. Nevertheless, its path brings it through the orbital plane of the solar system, where most planets and asteroids reside, so there is a natural question about whether it might collide with something. The main region of concern is the asteroid belt between Mars and Jupiter. The belt is not a solid ring of rocks, but a vast, sparse cloud of material. To the human eye, it appears empty, yet the question of collisions persists because people often envision it as dense due to science fiction films. As 3I Atlas approaches the zone, astronomers and the public alike wonder, will it survive this part of its journey intact? To answer that, one must understand the real nature of the asteroid belt. In popular culture, it is depicted as a dangerous obstacle course, where spacecraft must weave between tumbling boulders. The reality is far more benign. There are indeed millions of asteroids within the belt, including about 1.1 to 1.9 million objects larger than 1 kilometer, and many millions of smaller ones. But those objects occupy an enormous volume of space. On average, the distance between one asteroid and another is about 965,600 kilometers, 600,000 miles. This means that if you were standing on the surface of an asteroid in the belt, the nearest neighbor would likely be so small and so far away that you wouldn't see it without a telescope. Universe Today notes that because of this low density, the odds of a spacecraft crossing the asteroid belt colliding with an asteroid are less than 1 in a billion. Scientific American emphasizes that the average spacing between kilometer-size asteroids is several million kilometers, and that collisions between them are extremely rare. An average 1-kilometer asteroid may suffer only 1 collision every few billion years. NASA's Pioneer and Voyager spacecraft passed through the belt decades ago without incident. And in fact, mission planners have sometimes struggled to arrange close flybys of even one asteroid, because the chances of an accidental encounter are so low. This perspective radically changes our assessment of the risks. Even though there are millions of rocks in the belt, the emptiness of the region means that the probability of 3I Atlas hitting one is minuscule. The main belt is like a vast desert with scattered boulders hundreds of miles apart. Crossing it is more like driving on an empty highway than steering through a hailstorm. Yet the emptiness of the asteroid belt does not guarantee survival. There are still hazards. One is the possibility of small debris and dust that are not cataloged. A collision with even a pebble-size object at 61 kilometers per second would release an enormous amount of energy and could blast a chunk off the comet. Another hazard is gravitational perturbation. As 3I Atlas passes by Jupiter, the giant planet's gravity will alter its trajectory slightly. Even a small tug could change its speed or spin, potentially making it more prone to fragmenting if its internal structure is weak. Moreover, the comet is approaching perihelion, where it will be bathed in intense solar radiation. As the sun's heat penetrates its surface, ices trapped for billions of years will sublimate, turn directly from solid to gas. This outgassing can create jets that act like rocket thrusters, altering its motion unpredictably. If the jets are strong and unevenly distributed, they could cause the comet to tumble or even break apart. Astronomers have watched many comets disintegrate this way. For example, Comet C 2019 Y4 3I Atlas fragmented in April 2020 after experiencing increasing pressure from sunlight. There are also comets like Ison in 2013 that disintegrated during perihelion. The structural integrity of 3I Atlas is unknown. We do not know if it is monolithic or a loose rubble pile held together by weak gravity and frozen volatiles. Some scientists have speculated, most notably astrophysicist Avi Loeb, that the brightness pattern of 3I Atlas might indicate non-natural origins. He suggests the possibility that it could be a fragment of alien technology and posits a scenario in which an interstellar craft could deploy dust in front of it to detect and avoid rocks in the asteroid belt. This idea is highly speculative and not widely accepted, but it serves to remind us how little we truly know about such objects. The scientific consensus is that 3I Atlas is almost certainly a natural comet, but because it comes from another star system, its composition could differ from anything we have seen. Beyond the question of survival, why do we care so deeply about this object? The answer touches on multiple threads of curiosity. Interstellar objects are snapshots of distant planetary systems. They are the physical messengers of processes that happened around other stars long before our sun was born. By studying them, scientists can test theories about planet formation. For example, one can look at the ratios of water, carbon dioxide, and other volatiles in 3I Atlas to see whether they match the mix found in comets from our own Oort cloud. Differences might indicate that the comet formed closer to or farther from its parent star, or that the parent star had a different chemical composition. Even the presence or absence of certain molecules can hint at whether the comet formed in the warm inner disk or the cold outer disk of its home system. Comparing 3I Atlas to 2I Borisov and to comets from our solar system could reveal patterns or surprising anomalies. Another reason to pay attention is the potential for pristine material. Interstellar comets spend eons in cold, radiation-filled space, but they have never been heated by a star until they encounter our sun. Their internal ices might thus preserve the original chemistry of their birth environment. Sampling, or even closely observing such material, could refine models of how organic molecules form on icy grains. there is also a philosophical dimension. The knowledge that matter from other star systems is drifting into ours invites us to imagine our solar system as one bubble in a cosmic ocean filled with countless others. Each interstellar object is a tiny handshake between systems. It tells us we are not isolated. There is exchange, albeit rare and subtle. Every piece of data on 3i Atlas feeds into a larger story about the connectedness of our galaxy. As we begin this journey through the story of 3i Atlas, the central question, will it survive the asteroid belt, transforms from a simple yes or no query into a richer investigation. We have to understand the composition and structure of the object, the properties of the asteroid belt, and the dynamics of the solar system. We have to reconcile cinematic imagery with scientific reality. The outcome is not just a matter of physical survival, but of knowledge. If 3i Atlas remains intact through perihelion and emerges on the other side of the sun, telescopes around the world and in space will continue to observe it, gleaning spectral signatures and monitoring changes in brightness. If it disintegrates, we will still learn something, but some questions might remain unanswered until the next interstellar visitor arrives. Right now, as September progresses, 3i Atlas is just inside Jupiter's orbit, moving rapidly toward the sun. It is still visible to ground-based telescopes, but soon it will be too close to the sun to observe from Earth, only to reappear in December on the other side. In this brief span, we have the chance to collect data that could reshape our understanding of comets and planetary systems. There is suspense, but also a reminder of the patient nature of science. We can only observe and interpret. We cannot alter its path or destiny. This introduction sets the stage for the rest of our exploration. We have glimpsed the speed and alien origin of 3i Atlas, placed it in the context of the other two known interstellar objects, recounted its discovery and early observations, and confronted the misconceptions about the asteroid belt that the object must cross. We have considered the physical characteristics of the comet and the hazards it faces, from dust impacts to solar heating. We have acknowledged speculative ideas while grounding our narrative in measurements and established science. Above all, we have highlighted why this object matters, not because it threatens us, but because it offers us a unique chance to study material from beyond our solar system. Whether 3i Atlas survives its journey intact or leaves behind a trail of fragments, it will have added to our understanding. In subsequent chapters, we will delve deeper into the science of comets and asteroid belts, compare this visitor with its predecessors, and follow the ongoing observations as it approaches perihelion. For now, we pause to appreciate that we live at a time when a small band of observers around the globe can detect a piece of another star system and invite everyone to share in the wonder. As the sun set on the evening of June 14th, 2025, the NASA-funded 3i Atlas Survey Telescope in Rio Hurtado, Chile, quietly began its nightly routine. 3i Atlas is designed to find hazardous asteroids on short notice, so it scans huge swaths of sky looking for faint, moving points of light. On that night, the telescope's wide-field camera captured a tiny smudge that shifted slightly between exposures. The automated software flagged the point as a potential comet or asteroid, but nothing extraordinary. Over the next 2 weeks, 3i Atlas continued its vigil, taking images on June 18th, 20th, 25th, 26th, 27th, 28th, and 29th. Each time, the faint object crept slowly across the background stars. Because the observations were spread across days rather than hours, they hinted that this visitor was not bound to the sun. yet no one knew that at the time. 3i Atlas processed images by the hundreds, and the object did not stand out immediately, caltech.edu. The revelation came on July 1st, when 3i Atlas researchers Larry Deno and other team members ran their latest images through a moving object detection pipeline. The software calculated a preliminary orbit from the June 14th to 29th dataset and found that the object's path was not elliptical, but hyperbolic, the hallmark of an interstellar origin. George Hello, Associate Director for Caltech's Infrared Processing and Analysis Center and a co-investigator on the Zwicky Transient Facility, ZTF, said this shape was the giveaway. Unlike the closed ellipses of solar comets, a hyperbola never closes on itself and signals that the object will pass through the solar system only once. The news triggered immediate excitement. Only 2 other interstellar objects had ever been observed. 1I Oumuamua in 2017 and 2I Borisov in 2019. A third interstellar comet would offer the first opportunity to study a visitor with relatively fresh ices and a long observational arc. As soon as 3i Atlas published the detection, observers around the world checked whether any of their instruments had recorded the object before July 1. Within hours, Quanji Ye at the University of Maryland used a program he developed to comb through ZTF data. ZTF is a wide-field survey at Palomar Observatory with a camera that can cover the entire northern sky every 2 nights. Ye's program compares positions of known objects across successive images and flags, anything that does not match the catalog. On July 1st, while many colleagues slept, Ye discovered that ZTF had captured the same faint body on June 28th and 29th. Those pre-discovery images meant astronomers did not have to extrapolate solely from a few hours of 3i Atlas data. They could compute the orbit using observations separated by days. Ye sent an email to colleagues at the Minor Planet Center and 3i Atlas, cautioning that the object's motion looked hyperbolic, but that he wanted to double-check before announcing an interstellar origin. He stayed up until 2 a.m. on July 2nd, verifying the measurements. When he finally declared confidence in the hyperbolic fit, excitement rippled across astronomy forums and social media. The Minor Planet Center assigned the temporary designation A11PL3Z. Observers scoured archival data for additional pre-covery images. Amateur astronomer Sam Dean found 3i Atlas images from June 5th to 25th that had captured the object unknowingly. ZTF's database contained further detections between June 14th and June 21st. Each extra measurement lengthened the orbital arc from the initial 3 hours to 3 weeks. With this improved baseline, orbital calculations converged. The object's eccentricity exceeded 1, confirming it would never return to the solar system. Astronomers initially nicknamed it Comet 3. Once the International Astronomical Union's Small Body Designation Team reviewed the evidence, they formally named it the third interstellar object, 3i, and gave it the cometary designation C 2025 N1. While number crunchers refined the orbit, observers rushed to point telescopes at the newcomer. At discovery, 3i Atlas was roughly magnitude 18, too dim for the naked eye but accessible to professional observatories. It lay about 3.50 astronomical units, AU, from Earth and 4.51 AU from the Sun, in the constellation Serpens Cauda, moving toward Sagittarius. Observers at the Lowell Discovery Telescope in Arizona and Canada-France-Hawaii Telescope on Mauna Kea captured spectra on July 2nd that showed a marginal coma surrounding the nucleus. The coma's presence indicated that the object was actively releasing gas, a key distinction from the dry, rocky Oumuamua. Initial color measurements suggested a reddish hue. Over the next week, telescopes around the world, big and small, contributed data. The global network of amateur astronomers also took up the chase, using backyard telescopes to measure brightness and motion. Within 2 weeks, the Minor Planet Center had cataloged 122 observations from 31 observatories. News outlets seized on the story. Many headlines asked if the Interstellar Comet was on a collision course with Earth. Astronomers quickly dispelled those fears. Calculations showed that the comet would not approach closer than about 1.8 astronomical units, nearly 270 million kilometers. That is more than 400 times the distance to the Moon. The comet's closest approach to the Sun, or perihelion, would occur around October 30th, 2025, at about 1.4 astronomical units, just inside Mars's orbit. In other words, it was not a threat, but an opportunity. The next stage in the story involves why this object was detected at all. George Hello pointed out that, compared to 2017 when Oumuamua slipped past with little warning, there are now more wide-field survey cameras scanning the sky. 3i Atlas itself is a pair of 0.5-meter telescopes with extremely wide fields of view. It is designed to find hazardous asteroids days before impact. The Zwicky Transient Facility uses a 48-inch Schmidt telescope with a 47-square-degree camera that can scan the northern skies rapidly. Other facilities like Pan-STARRS, the Catalina Sky Survey, and dozens of smaller surveys collectively act as an early warning network. This infrastructure did not exist just a decade ago. It explains why the first interstellar object, Oumuamua, was not spotted until 2017, and why we have found 2 more within 8 years. The simple but profound implication is that interstellar visitors may be common, but we have only recently gained the technological ability to detect them. As the data trickled in, astrophysicists began to characterize 3i Atlas. One of the first questions was its size. Without a close-up spacecraft, scientists have to infer size from brightness and albedo, reflectivity. Early estimates varied widely, with some speculating the nucleus could be tens of kilometers across. On August 20th, NASA released a more constrained estimate based on Hubble Space Telescope measurements. The nucleus is at least about 440 meters in diameter and no larger than about 5.6 kilometers. Even at the upper end, 5.6 kilometers makes it large compared with typical short-period comets, but not unprecedented. The uncertainty reflects how quickly the comet's brightness changed as it released gas and dust. Another crucial parameter is the comet's speed. At discovery, it was moving about 61 kilometers per second relative to the Sun. Such velocity is typical for bodies ejected from other star systems, but it means the comet will spend little time near any particular region of the solar system. Because of its high speed, the object's passage through the main asteroid belt between about 2.2 and 3.2 astronomical units will occur in just a few months. That is why early pre-covery images were so valuable. They give astronomers a longer baseline to predict where the comet will be when large telescopes or even spacecraft might observe it. The longer the baseline, the smaller the positional uncertainties. With confirmation of the comet's interstellar nature, scientific interest skyrocketed. NASA, the European Space Agency, and various research groups coordinated observation campaigns. Planned instruments included the Hubble Space Telescope and the James Webb Space Telescope for high-resolution imaging and spectroscopy, the Transiting Exoplanet Survey Satellite for photometric monitoring, the Swift Observatory for ultraviolet and X-ray observations, and the SphereX mission for infrared spectroscopy. Even planetary missions like the Mars rovers, Perseverance and Curiosity were slated to attempt photography of the comet when conditions allowed. Earth-based radio telescopes prepared to measure the comet's emission lines to infer its composition. The extensive interest stems from the possibility that 3I Atlas could provide a chemical fingerprint of another star system's protoplanetary disk. The excitement also extended to speculative ideas. Avi Loeb, an astrophysicist known for suggesting extraterrestrial origins for Oumuamua, noted that if 3I Atlas were an artificial probe, its high speed might allow it to traverse the asteroid belt quickly, and he mused about whether it might deploy a dust buffer to detect obstacles. Most scientists dismiss these musings as extremely unlikely. Nonetheless, they highlight how interstellar objects capture imaginations. For the majority of astronomers, 3I Atlas is of interest precisely because it is natural. Its volatiles may tell us whether other star systems have similar chemical abundances to our own. Observing the isotopic ratios of hydrogen, carbon, nitrogen, and oxygen in its gas could test models of planet formation. If those ratios differ significantly from solar system comets, it might indicate that the comet formed closer to or farther from its parent star than typical Oort cloud objects. On the other hand, a close match would support the idea that protoplanetary disks across the galaxy have comparable compositions. The ability to track the comet for several months before perihelion also allows astronomers to study its activity as the sun heats it. On July 2nd, only one day after the discovery, a marginal coma was detected, meaning some gas and dust was already escaping. As the comet approaches the sun, the flux of sunlight increases, causing more volatiles to sublimate and potentially leading to jets of gas that can alter the comet's rotation. Observers will watch for brightening events, fragmentation, and changes in tail morphology. Because 3I Atlas will never return, any evolution we witness is unique. This is why many teams scheduled repeated observations rather than one-time snapshots. An often overlooked aspect of the discovery story is the human collaboration behind it. 3I Atlas, ZTF, Pan-STARRS, and other survey teams coordinate their data processing pipelines and share candidate lists. The Minor Planet Center acts as a clearinghouse, posting new objects and orbits. Amateur astronomers contribute by providing additional astrometry and by discovering pre-covery images in public archives. When Ye found the ZTF pre-discovery images and stayed up late verifying the orbit, he demonstrated the dedication common in this field. His caution in not claiming an interstellar origin until the data were solid also illustrates the scientific method. Meanwhile, Sam Dean's success in locating earlier 3I Atlas images shows the value of citizen scientists in archival research. The subsequent flood of observations from 31 observatories underscores the global nature of cometary research. Dozens of research groups, spanning continents and time zones, coordinate their schedules to sample different wavelengths, times of day, and instrumentation. In the weeks after the discovery, the story of 3I Atlas reached a wider public. Media outlets explained what an interstellar object is and how rare it is to witness one. Articles emphasized that the comet posed no threat to Earth and that its passage through the asteroid belt would not be like science fiction. When asked why such objects are only now being found, astronomers pointed to the proliferation of large-format cameras scanning the sky. They noted that improved computing power and machine learning algorithms allow them to sift through terabytes of data quickly. They also highlighted how earlier discoveries spurred interest and funding, enabling even more comprehensive surveys. In this sense, each interstellar object detection feeds into the next, creating a virtuous cycle of technology development and curiosity. By mid-July 2025, the initial adrenaline rush gave way to methodical work. Observers continued to monitor the comet's brightness, noting periodic spikes as jets of gas burst from its surface. Spectroscopists looked for emission lines of water, carbon monoxide, and cyanide. Dynamical modelers refined the orbit using the growing dataset, reducing uncertainties in predicted positions months ahead. Planetary scientists debated whether to propose a rapid flyby mission, though the timelines are likely too short. In August, NASA Hubble release put the size estimates on firmer footing, leading some researchers to compare 3I Atlas with 2I Borisov, which had a nucleus about 1 kilometer across. They noted that if 3I Atlas is closer to the 440-meter estimate, it might be more susceptible to fragmentation near perihelion. Conversely, if it is nearer the 5.6-kilometer upper bound, it could survive, giving scientists a longer post-perihelion window. Every step of this process highlights how astronomy has changed. In 1910, Halley's Comet thrilled the world, but the data were limited to optical photographs and human eye observations. A century later, an interstellar comet triggers coordinated campaigns across the electromagnetic spectrum, using both ground-based and space-based instruments. The data will reside in publicly accessible archives, allowing researchers for decades to reanalyze them as new techniques emerge. The speed with which 3I Atlas was identified as interstellar, within hours of discovery, also underscores the power of modern networks. The collaboration between 3I Atlas and ZTF, emphasized by the quick identification of pre-discovery images, reveals how different surveys complement one another. By early September 2025, 3I Atlas was steadily brightening, crossing the orbit of Jupiter and heading toward Mars' orbit. Observers watched for the development of a tail. Some amateur images already showed a faint streak. News articles reminded readers that the comet would not be easily visible without a telescope, and that the best views would likely come after it emerged from solar conjunction in December. Nevertheless, the sense of wonder remained. Each new image posted to social media brought comments like, "A messenger from another star," or "The galaxy sending us a postcard." These phrases capture why the story of 3I Atlas resonates beyond astronomy. In a world full of earthly concerns, the arrival of a chunk of ice from beyond the sun's influence offers a reminder of the vastness of our universe. As we close this chapter, we stand in the middle of the story, not at the end. The comet has been recognized, its origin traced, and its path predicted. Telescopes are poised to monitor its approach to perihelion. Scientists have plans to measure its composition, and the public has a narrative that combines cosmic adventure with the rigor of modern science. The outcome, whether 3I Atlas survives its close brush with the sun or breaks apart, is unknown. What is already clear is that the discovery has advanced our understanding of interstellar debris and strengthened the community that studies such phenomena. When the next interstellar object appears, we will be even better prepared to seize the fleeting opportunity to learn about another corner of our galaxy. The chapter opens by shifting the focus from the excitement of discovery to the more careful work of understanding what kind of object 3I Atlas is and how it compares with previous interstellar visitors. early observations left astronomers unsure whether the newcomer was a rocky asteroid or an icy comet. It moved fast, like one-eye Oumuamua, but seemed faint and fuzzy in telescopic images. Within days, however, multiple telescopes confirmed a tenuous cloud of gas surrounding the nucleus, a sign of cometary activity. This faint coma, visible even when the comet was still 4.5 astronomical units from the Sun, signaled that sunlight was warming ices on the surface and releasing gas and dust into space. That behavior, together with the discovery circumstances, led the Minor Planet Center to designate the object C 2025 N1, 3I Atlas. It also received the title 3I because it was only the third interstellar object ever confirmed. From that point on, 3I Atlas was treated as a comet, one not born of our solar system, but possessing ices from another star. One of the first physical questions astronomers asked was how big the comet's nucleus might be. Brightness alone cannot answer this, because reflected sunlight depends on size and reflectivity, and a growing coma can hide the nucleus. Initial estimates ranged wildly, from a few hundred meters to 20 kilometers, partly because the comet's activity varied as it drew nearer to the Sun. Observations by the Hubble Space Telescope on 21 July 2025 provided a much clearer view of the coma and allowed scientists to constrain the nucleus's diameter to below 5.6 kilometers. The lower limit, based on how bright the comet remained even before a large dust cloud formed, was about 440 meters, a range similar to or a bit larger than that of the first two interstellar objects. Thus, 3I Atlas is likely a kilometer-scale body, bigger than Oumuamua and comparable to 2I Borisov. Its moderate size means that while it contains significant mass, it is not so large that its discovery challenges theoretical expectations of interstellar object sizes scientificamerican.com. The next major question involves the comet's composition. What ices does it contain, and do they reveal anything about its place of origin? As 3I Atlas moved inward, space-based observatories trained their spectrometers on the coma. In mid-August, NASA's SPHEREX mission detected a bright carbon dioxide emission and a signature of water ice in the gas cloud. The detection suggested that the comet's coma is unusually rich in CO2 relative to water, a striking contrast with most solar system comets, which are dominated by water vapor. Later observations by the Very Large Telescope, VLT, not only confirmed this carbon dioxide dominance, but also detected cyanide gas and atomic nickel vapor at concentrations similar to those in solar system comets. The presence of nickel vapor implies that 3I Atlas contains metal-rich dust grains that are vaporizing in the heat of the Sun, another common feature in comets. Astronomers also noted small amounts of water vapor, carbon monoxide, and carbonyl sulfide in the coma. The chemical mix hints that 3I Atlas formed far from its parent star, beyond the carbon dioxide frost line where volatile CO2 can freeze. A solar system analog is the Oort cloud. If so, the comet's present-day composition is a fossil record of a distant protoplanetary disk. More intriguing still is the object's possible age. Because interstellar comets are not bound to their stars, their origins are often lost to time. However, by combining its extremely high velocity relative to the Sun, about 58 kilometers per second as it entered the solar system, with models of galactic dynamics, some researchers have proposed that 3I Atlas could have come from the Milky Way's thick disk. The thick disk is a component of our galaxy populated by old stars moving at high velocities above and below the galactic plane. If 3I Atlas originated there, it may be more than 7 billion years old, predating our own solar system. Such an ancient interstellar wanderer would have been traveling the galaxy for eons, collecting radiation damage and perhaps losing superficial volatiles. By contrast, 2I Borisov, with its high abundance of carbon monoxide and lack of water, seemed relatively young. Determining whether 3I Atlas is indeed a thick disk relic requires careful analysis of its composition and trajectory, but the mere possibility underscores the object's scientific value. Beyond composition and age, the comet's dynamics set it apart from previous interstellar visitors. Every orbit in space is defined by an eccentricity, a number describing how stretched its path is compared with a circle. Elliptical orbits have eccentricity less than 1. Parabolic orbits equal 1. Hyperbolic orbits exceed 1. The trajectory of 3I Atlas has an eccentricity of about 6.14, far beyond the values for Oumuamua, 1.2, or Borisov, 3.4. This means the comet's path through the solar system is almost straight, a fleeting flyby rather than a loop. 3I Atlas is the most extreme interstellar object yet, moving faster and taking a less curved path than its predecessors. It will pass inside Jupiter's orbit, slice through the asteroid belt, skim just inside Mars's orbit at 0.19 astronomical units on the 3rd of October, 2025, reach perihelion at 1.36 astronomical units on the 29th of October, 2025, cross Venus's orbit a week later, then traverse back out of the solar system, coming 1.8 astronomical units from Earth on the 19th of December, 2025. Despite its speed, gravitational interactions with the planets will hardly slow it. Once it leaves, we will never see it again. This high velocity raises a practical question. What happens when the comet enters the region between Mars and Jupiter, known as the main asteroid belt? Popular culture often depicts the belt as a congested gauntlet of tumbling rocks through which spacecraft must dodge and weave. In reality, the belt's objects are separated by immense distances. Universe Today notes that although there are millions of asteroids in the main belt, the average distance between them is roughly 965,600 kilometers, 600,000 miles. That is more than twice the distance between Earth and the Moon. Because the belt is spread over a thick, torus-shaped volume about 1 astronomical unit deep, the odds of a collision with a lone comet passing through are estimated to be less than 1 in a billion. Spacecraft such as NASA's Pioneer, Voyager, and New Horizons have safely crossed the belt without any special evasive maneuvers, and 3I Atlas will do the same. Its crossing will take only a few months, and given the emptiness of the region, the risk of hitting an asteroid is negligible. The real challenges for 3I Atlas are gravitational and thermal, not collisional. Gravitational perturbations arise mainly from Jupiter, whose enormous mass can deflect comets into new orbits. In the case of 3I Atlas, the encounter with Jupiter occurs after perihelion, when the comet is already heading outward. Simulations show that the closest approach to Jupiter, about 0.36 astronomical units on the 16th of March, 2026, will alter the comet's speed slightly, but not enough to bind it. The comet's hyperbolic excess velocity of 58 kilometers per second ensures that Jupiter's tug remains a minor perturbation. Tidal forces from the Sun could be more significant as the comet swings around perihelion. When comets approach the Sun, intense heating causes sublimation of surface ices. Jets of gas can create torques that change the spin rate and stress the body. Cometary nuclei are often rubble piles, loose agglomerations of ice and rock held together weakly by gravity and frozen volatiles. If internal pressures exceed the cohesion of the material, a comet can split. Several comets, such as C2012 S1 ISON and C2019 Y4 3I Atlas, have disintegrated near Perihelion. For 3I Atlas, its moderate size and unknown structure make predictions difficult. Observers hope that by monitoring changes in brightness and the development of jets, they can infer how internal stresses evolve as the comet warms. Another distinctive feature of 3I Atlas is its color. Early observations noted a reddish hue in its coma, similar to the colors of 2I Borisov. In solar system comets, reddish dust often indicates organic compounds or complex hydrocarbons on the surface. As the comet approaches the sun, changes in color might reveal surface evolution. Fresh ice may be exposed, or different grain sizes might dominate. A study published by Tony Santana Rose and colleagues in August 2025 found that 3I Atlas's coma became redder over July, suggesting that the composition of the dust and gas was changing as the comet's activity increased. Tracking such changes provides clues about the layering of materials within the comet and the sequence in which different volatile species sublimate. Comparisons with the two previous interstellar objects deepen our understanding of these rare visitors. Oumuamua, detected in 2017, was mysterious because it displayed no coma, changed brightness dramatically, and accelerated anomalously as it left the solar system. Its shape was inferred to be highly elongated or pancake-like, and its composition remains debated. Borisov, discovered in 2019, looked more like a typical comet with a bright coma and tail. Yet spectroscopic measurements showed an unusual chemistry with hardly any water, but abundant carbon monoxide and hydrogen cyanide. 3I Atlas occupies a middle ground. It is active but not yet vigorously so. It shows a dense carbon dioxide coma and water ice, hinting at a composition distinct from both Borisov and solar comets, and it possesses an extreme trajectory and speed. Together, these three objects demonstrate that interstellar visitors are diverse, each likely formed in different types of protoplanetary disks and experienced different ejection mechanisms. Oumuamua may have been a fragment of a tidally disrupted planetesimal. Borisov may have come from a young disk rich in carbon monoxide. 3I Atlas may hail from an older, cold region where carbon dioxide dominates. While the object's composition is of prime scientific interest, its rotation and shape also matter. The rotation period of 3I Atlas remains uncertain, but astronomers hope to deduce it by monitoring variations in brightness. If the comet spins quickly, jets may be smeared over its surface. If slowly, the heating might be uneven, causing one hemisphere to erupt more violently. The shape could be spherical, elongated, or irregular. Each carries information about formation and collisional history. A steady, rapid rotation might suggest ejection by a close encounter with a massive planet in the comet's home system. By contrast, a slow spin could imply a more gentle ejection, perhaps through stellar mass loss. Observers plan to use the Lowell Discovery Telescope, which can observe the comet near sunrise or sunset, to measure light curves even when the comet is close to the sun. The comet's upcoming encounters with planets also provide observational opportunities. On the 3rd of October, when the comet passes within 0.19 astronomical units of Mars, spacecraft orbiting the red planet, such as MAVEN, may be able to image the comet and measure its coma from a different perspective. Such observations can complement Earth-based data and help determine how the coma extends in 3 dimensions. After perihelion, the comet will swing past Venus at 0.65 astronomical units on the 3rd of November and cross Earth's orbital distance at 1.8 astronomical units on the 19th of December, though Earth will not be nearby. These flybys will not influence the comet's orbit significantly, but they serve as convenient markers for planning observations. As the chapter concludes, the narrative emphasizes why all these details matter. Understanding 3I Atlas's size, composition, color, and trajectory is not mere cataloging. It informs broader questions about how planetary systems form and evolve. The dominance of carbon dioxide suggests that protoplanetary disks in other star systems can have different temperature structures. The potential thick disk origin implies that comets can survive for billions of years, traveling from one star environment to another. The extreme hyperbolic orbit shows that high-velocity ejections do occur, perhaps through encounters with giant planets or close stellar flybys. And the fact that 3I Atlas will pass through the asteroid belt unharmed reminds us that space, even within the busy regions of our own system, is mostly empty. In the next chapter, attention will turn to what happens when the comet reaches perihelion. How intense heating may trigger spectacular activity, whether the nucleus can hold together, and what scientists hope to learn from the outburst of gas and dust. After the frantic weeks following its discovery, astronomers began to look more closely at what makes 3I Atlas extraordinary. The first clue is its appearance. Unlike the rocky, inert Oumuamua or the faintly active 2I Borisov at discovery, 3I Atlas quickly showed a dusty coma and a hint of a tail. Observations on July 2, 2025 by multiple telescopes, including Chile's Deep Random Survey, Arizona's Lowell Discovery Telescope, and the Canada-France-Hawaii Telescope, revealed a diffuse envelope of gas and dust around its nucleus with a reddish tint. That reddish hue is similar to 2I Borisov and suggests that sunlight is reddening dust particles expelled from the surface. Within days, astronomers were confident the object was not a bare rock, but a comet. The cometary designation C 2025 N1 3I Atlas and the interstellar tag 3I were soon added to its name. Suddenly, there was a new member of a tiny family, the third interstellar comet known to science. As researchers measured the comet's brightness and motion, they refined estimates of its size and speed. The Hubble Space Telescope's July 21st images showed a compact nucleus with a well-developed coma, allowing scientists to constrain the diameter of the solid nucleus to below about 5.6 kilometers. Later analyses indicated it might be as small as 1 or 2 kilometers, similar to typical solar system comets, but much larger than Oumuamua and somewhat comparable to 2I Borisov. The comet's speed, however, is unprecedented. When 3I Atlas entered the solar system, it was already moving at approximately 58 to 61 kilometers per second relative to the Sun. By perihelion on 29th of October, 2025, it will accelerate to about 68 kilometers per second. This hyperbolic motion translates to a trajectory with an eccentricity of around 6.14, so high that the path appears almost straight in orbital diagrams and far exceeds the eccentricities of Oumuamua, E approximately 1.2, and Borisov, E approximately 3.4. The comet's orbit is retrograde, tilted about 175 degrees relative to the plane of the planets, and just 5 degrees out of the ecliptic. These parameters confirm the object came in from a random direction and will not be captured by the Sun's gravity. After one passage, it will leave for interstellar space. What has really captivated scientists is the chemistry locked inside this interstellar ice ball. Early ground-based observations hinted at a reddish coma, but space-based instruments soon provided more tantalizing data. SphereX, NASA's near-infrared mission, observed 3I Atlas between 7 and 15 August 2025 and reported a coma rich in carbon dioxide and containing water ice. The ratio of carbon dioxide to water appears unusually high compared with typical solar system comets, suggesting that 3I Atlas formed beyond the CO2 frost line in its home system. JWST observations released at the end of August confirmed the presence of carbon dioxide and small amounts of water vapor, carbon monoxide, and carbonyl sulfide. Meanwhile, the Very Large Telescope detected cyanide gas and atomic nickel in the comet's coma at concentrations similar to those in solar system comets. These molecules are key tracers of temperature and irradiation history. Cyanide and nickel indicate that the comet's surface has been processed by cosmic rays, but that its interior may remain pristine. The dominance of carbon dioxide could mean the comet formed far from its star, where water ice could freeze and carbon dioxide could condense easily. The chemistry also hints at an ancient origin. Astronomers used 3I Atlas's unusually high space velocity to infer possible birthplaces. One team suggests the comet may have come from the Milky Way's thick disk, a component of older stars that orbit above and below the galaxy's main plane. If that is the case, 3I Atlas might be 7 billion years old or more, older than our solar system. Another analysis estimated an age between 3 and 11 billion years based on trajectory modeling. In either case, this comet is likely a relic of planet formation in a star system that no longer exists. The possibility that we are sampling ice from a bygone world adds poignancy to the mission of studying it. Researchers will look for isotopic ratios of hydrogen, carbon, and nitrogen to learn whether other star systems have similar chemistry to our own. Comparisons with the first two interstellar objects help frame expectations. 1I Oumuamua, discovered in 2017, showed no coma and had an elongated or perhaps disc-shaped body. It tumbled and accelerated as if propelled by radiation pressure or gas leaks. Its lack of volatiles made some speculate it was a fragment of a larger body or even alien technology. 2I Borisov, discovered in 2019, looked more like a normal comet, but had an unusual composition: little water and abundant carbon monoxide and hydrogen cyanide. Borisov's nucleus was about 1 kilometer across and had a fairly low speed, making it possible to track for several months. 3I Atlas seems intermediate. It is active like Borisov, but appears to contain more carbon dioxide than Borisov, and may be larger. Its speed is almost double Borisov's, leaving less time for study. These three objects already hint at a diversity of interstellar debris. Some pieces may be fragments of planets, others are comets from the outer regions of alien systems. Each new object widens our understanding of what is drifting through the galaxy. Understanding 3I Atlas's path through the solar system is key to addressing the video's central question: will it survive the asteroid belt? From mid-2025, it has been moving inward. It crossed Jupiter's orbit in July and will pass by Mars at about 0.19 astronomical units on the 3rd of October, 2025. then reach perihelion at 1.36 astronomical units between Earth and Mars on the 29th of October. After perihelion, it will swing past Venus at 0.65 astronomical units on the 3rd of November, pass near Earth at 1.8 astronomical units on the 19th of December, and finally cross Jupiter's orbit again in March 2026. The comet's trajectory is nearly aligned with the ecliptic, meaning it will thread through the region where most planets and asteroids orbit. But because it spends only a few months in the inner solar system and its orbit is retrograde, its encounters with large bodies are brief and distant. Computer simulations show that its passage near Mars and Venus will not perturb their orbits significantly, and it will never come closer than about 268 million kilometers to Earth. The portion of its journey that prompts the most curiosity, and the title of this video, is its traversal of the asteroid belt. Many of us picture this zone as a dense swarm of tumbling rocks that would smash anything passing through. In reality, the main belt is a vast region of mostly empty space. Although it contains millions of asteroids, they are spread over a volume hundreds of millions of kilometers across. Universe Today notes that the average distance between kilometer-sized asteroids is about 965,600 kilometers, more than twice the distance from Earth to the Moon. Because the material is so sparse, the odds of a spacecraft or comet colliding with an asteroid while crossing the belt are less than 1 in a billion. This is why spacecraft like Pioneer, Voyager, and New Horizons have sailed through unscathed. 3I Atlas moves so fast that it will spend only a few months in this region, further reducing the chance of an encounter. Even though there are an estimated 1.1 to 1.9 million asteroids larger than 1 kilometer, and many smaller ones, they occupy a volume so large that collisions are exceptionally rare. So the real perils facing 3I Atlas are not asteroid impacts, but thermal stresses and gravitational tides. As the comet approaches perihelion, solar radiation will warm its surface. Volatile ices that have been stable in the cold of interstellar space for billions of years will sublimate into gas. This outgassing can create jets that act like thrusters, potentially spinning the nucleus or altering its trajectory slightly. If the nucleus is loosely bound or contains internal fractures, it could break apart under thermal stress. Many solar system comets have met such fates. Comet C 2012 S1 ISON disintegrated as it approached the Sun in 2013, and Comet C 2019 Y4, 3I Atlas, fragmented in 2020. Whether 3I Atlas will survive depends on its size, internal strength, and heat transport properties. A larger, more cohesive nucleus may withstand the heat, while a small rubble pile might crumble. Observers will watch for signs of fragmentation in September and October as the comet's activity increases. The SphereX and JWST detections of carbon dioxide and water suggest that significant outgassing is already happening, so a dramatic increase is likely. Even if the nucleus fragments, the fragments may continue on similar trajectories. From a scientific perspective, a breakup could be a boon. Exposed interior material would reveal the pristine composition of the comet's core. Spectrographs could sample molecules that were previously hidden. If the nucleus survives, it will provide data over a longer period as it recedes from the Sun. Either outcome enriches our understanding of interstellar comets. Scientists are especially keen to see whether 3I Atlas's carbon dioxide-dominated composition persists as it warms, and whether it releases organic molecules. JWST's infrared spectrograph will search for water, carbon monoxide, ammonia, and other volatiles. Hubble plans ultraviolet spectroscopy in November to probe the sulfur to oxygen ratio and other elemental abundances. Observations from Mars orbiters such as MAVEN may capture images as the comet passes by Mars in early October. On Earth, ground-based telescopes like Lowell's Discovery Telescope will continue to monitor brightness and coma morphology during dawn and dusk when the comet is visible. The emptiness of the asteroid belt also underscores a broader point. Our mental images of space often lag behind reality. Popular culture tends to depict the belt as a dense gauntlet, but the facts show it is mostly vacuum. This misunderstanding extends to interstellar comets as well. Some media outlets speculated that 3I Atlas might be an alien spacecraft. Astrophysicist Avi Loeb proposed that a high-speed interstellar craft might deploy dust or gas to detect obstacles. While he did not claim 3I Atlas was artificial, his comments fueled speculation. The scientific consensus is that 3I Atlas is natural. Its composition and activity are consistent with a comet, and there is no evidence of propulsion or maneuvering. The extraordinary thing about 3I Atlas is not that it is artificial, but that nature produced it and delivered it into our view. Ultimately, the question, will 3I Atlas survive the asteroid belt, illuminates more about human curiosity than about real danger. Statistically, the comet will cross the belt without incident. The real drama will unfold as solar heat tests the integrity of a body that has been cold for billions of years. Whether it remains intact or sheds pieces, 3I Atlas will have accomplished something remarkable. It will have connected us to the wider galaxy. By sampling its gases and tracing its trajectory, we gain insight into star systems that existed long before ours. The object's very existence hints at the dynamic processes that eject comets into interstellar space, and at the mixing of material between star systems. In the few months that it is visible, 3I Atlas invites us to look up, to think about timescales longer than human history, and to appreciate that our solar system is not isolated. The emptiness of the asteroid belt may offer safe passage, but the real test, survival in the sun's furnace, will determine how long we can watch this emissary from afar. Regardless of the outcome, 3I Atlas expands our cosmic horizons and prepares us for the next interstellar traveler who will someday follow. The sun is no passive bystander. It is a roaring furnace of plasma, a seething sphere of nuclear fire, and anything that dares to wander too close is transformed. For 3I Atlas, the interstellar visitor, this was the crucible where it would reveal its true nature. As it plunged deeper into the inner solar system, sunlight no longer trickled across its surface. It assaulted it. Each second, radiation blasted into the comet's icy shell with an intensity thousands of times stronger than it had endured in the frozen abyss between stars. Temperatures rose, pressure built, and like a sleeper waking from a billion-year dream, the object began to stir. Jets erupted, not small trickles, but geysers, fountains of gas and dust blasting from cracks in the crust, venting invisible ices into glowing plumes that streamed away into space. Through telescopes, the once dark rock was now haloed in a coma of shimmering gas, its profile swollen into something ghostly and alive. It was no longer a point of light. It had become an apparition. Astronomers strained to capture every frame of the drama. Observatories in Chile, Hawaii, and Spain tuned their instruments to the spectral fingerprints of water, carbon monoxide, cyanide. The data revealed a composition unlike any catalogued comet. Ratios were skewed. Trace elements appeared where none should be. The sun, acting as interrogator, was forcing the object to speak its secrets in chemical smoke. And then came the tails. Dust, lifted by the torrent of escaping gas, streamed behind the comet in a pale golden ribbon, stretching millions of kilometers into the void. Beside it, thinner and more elusive, a second tail shimmered. The ion tail, driven not by sunlight but by the solar wind, a gale of charged particles sweeping outward from the sun. This one was blue, electric, writhing like a whip as magnetic fields bent it. Two tails, twin signatures of cometary life. Yet in 3I Atlas, there seemed hints of a third, faint, anomalous emissions that no model predicted, glowing faintly green in ultraviolet filters. The world watched. News outlets ran breathless reports. An alien comet reveals strange new chemistry. Panels of scientists debated live, their voices edged with awe and disbelief. Was this interstellar visitor bearing chemical recipes from another system? Was it delivering molecules never seen before in our cosmic neighborhood? For a moment, humanity looked up together, caught in the shared wonder of something that came from beyond. But wonder was not the only emotion. As activity intensified, the comet's trajectory appeared to wobble. Not by much, fractions of a degree, but enough for orbital analysts to notice. Sublimation, the process of venting gas, acted like thrusters, subtly nudging its path. Predictions had to be recalculated daily. Would it disintegrate before reaching perihelion, the moment of closest approach to the sun? Would it survive the fiery ordeal? Or worse, would fragments scatter, some aimed uncomfortably close to Earth's orbit? The story deepened. On one night in late March, the Solar and Heliospheric Observatory captured something extraordinary. A burst of light flaring off the comet's core, brighter than any jet. For hours, the coma expanded violently, swelling like a balloon. Then, almost as suddenly, it contracted. Some astronomers argued it had fractured, one body becoming several. Others insisted it was a giant outburst, a single massive exhalation of volatile gases. Either way, the object was no longer behaving like a silent rock. It was thrashing, unpredictable, as though the sun's heat was awakening not just chemistry, but something deeper, stranger. And then, the close pass. At perihelion, 3I Atlas skimmed just inside the orbit of Mercury, where sunlight is a brutal hammer and the solar corona lashes outward in storms. For days, telescopes worldwide had waited for this moment, braced for the possibility of a spectacular breakup. Would the object shatter like icon before it, dissolving into a ghostly smear? Or would it endure, scarred but whole? The images that came back were almost cinematic. The comet's head blazed, brighter than expected, the coma expanding into a luminous shroud. Its tail stretched like banners in battle, rippling in the solar wind. Solar flares erupted nearby, tongues of plasma reaching outward, as if the sun itself was striking at the intruder. But the visitor did not vanish. When the glare cleared, it was still there, diminished, yes, fragments possibly trailing, but intact enough to continue its path outward. For the scientific community, this survival was priceless. It meant more data, more weeks to study emissions, more chances to track how interstellar ices behaved in the furnace of our star. But for those outside the labs, the imagery carried a different weight. People saw an alien wanderer defying annihilation. They saw resilience, almost defiance, and it stirred something primal: fear, awe, reverence. The comet had endured where few others had. And then came the whispers. Amid the spectral data, researchers noticed patterns, emission lines that repeated in intervals too regular, too orderly. Some dismissed them as calibration errors. Others, more cautious, wondered aloud, was this just chemistry or something more? Could a comet carry structure, not just randomness? The sun's heat had forced it to bear its inner makeup, and what it revealed seemed deliberate. Headlines shifted tone. "The comet speaks," one outlet declared. Another, more sober, warned against anthropomorphism, but admitted the oddities were difficult to reconcile. Forums exploded. Was this merely exotic chemistry, or could it hint at something designed? The sun had turned the interstellar object into a spectacle, a burning question mark against the void. Its activity was not just astronomical, it was theatrical. Every outburst, every tail flick, every spectral line fed the sense that this was not just a comet, but a messenger. And if it was a messenger, then the question was clear. What was it trying to say? For now, humanity could only watch as the visitor began its retreat, swinging away from the sun, outbound once more. Its brilliance faded slowly, but the mystery had only deepened. In the fire near the sun, 3I Atlas had revealed itself not as a silent traveler, but as something louder, stranger, more unsettling than anyone had imagined. And far beyond the cameras, beyond the chatter of scientists and the fears of the public, the comet continued its journey, leaving behind a trail of light, a signature, a riddle, a promise that the story was far from over. The sun fell behind it like a closing furnace door. Where heat had howled at 3I Atlas, there was now a long, cooling hush, the kind of silence you feel in your bones after a storm. The comet's incandescent veil thinned. Its broad, battle-scarred coma shrank with each passing day. But the struggle had left a record written in light. Lacy streamers of dust unfurled behind it, arcs within arcs, memory etched into motion, curves telling the story of outbursts no telescope had fully seen, of jets that had kicked and spun and nearly unmade the traveler in the sun's grasp. It was different now. The radiant bravado of its inward plunge gave way to a lean, taut grace. You could see it in the way the tail held its line, in how the ion ribbon flicked and settled as though the comet were breathing slower. The great torch was dimming, yes, but the ember was still hot. And in that ember, astronomers said, was the best of the science. Near the sun, everything shouted. Photons hammered, gas boiled, models broke. Outbound, the comet spoke in full sentences, still poetic, but patient enough to read. Behind it, like a living wake, trailed the evidence. Dust of many sizes, some grains as soft as cigarette smoke, others as gritty as beach sand. Under the pressure of sunlight, the smallest grains peeled away fast, curving outward into a delicate fan. Heavier motes clung to the spine of the tail, as if reluctant to let go. Hidden in the glow were seeds of carbon, flecks of silicate, veneers of organic frost, scraps from a nursery that whirled around a star too distant to name. Each speck was a syllable from another system's genesis, flung into the dark and, for a while, illuminated by our fire. The world had learned to point everything at 3I Atlas, radios listening for ions, spectrographs combing for fingerprints, cameras raking for ripples. Now, on the far side of the inferno, the choreography shifted. Telescopes no longer braced for shock, but coordinated like a choir. Night after night, they recorded the soft fade, a coma draining of its fury, a nucleus that, if fractured, held its pieces close like a flock after a hawk's pass. A cadence set in, measure, compare, infer, revise, until the comet's light curve read like a heartbeat in recovery. On the red planet, Steel Eyes waited, as 3-Eye Atlas's outbound road carried it past Mars's orbit. Instruments that had stared across rusty plains toward blue-white stars now pivoted to catch a stranger's afterglow. The planet's thin air offered no help. This was not a thing to taste, only to witness. But even a distant glimpse mattered. Some swore the images caught subtle changes in the jet pattern, as though vents had refrozen and new ones opened like night-blooming flowers. Others saw the ghost of a fragment tucked into the dust, a pale lump lagging in the wake like a child's kite at dusk. If true, it was less a wound than a shed skin, a reminder that survival near the sun is never the same as returning unchanged. From the dark between planets, other craft joined the vigil. Slender machines, busy with their own odysseys, stole moments to cross the comet's exhalations. Dust counters ticked, the soft, statistical rain of grains tapping, sensors with whisper-light impacts. Magnetometers quivered as the ion tail brushed past, a taut blue banner tugged by the solar wind's invisible hand. In those numbers, the outward fading comet drew its final self-portrait. Density dropping, temperature easing, chemistry relaxing into equilibrium as sunlight dwindled. The orchestra had moved from fortissimo to a lingering diminuendo. And yet, for all the scientific neatness, the comet refused to be dull. There were nights when the brightness pulsed, a timid echo of the violent surges near the sun, as if internal heat was trapped and released in sighs. There were edges of the tail that kinked and stitched themselves flat again under sails of radiation pressure. Sometimes the ion ribbon, normally a spear-like arc, developed a ripple that marched along its length in step with the sun's breath. Space weather, the experts said, the heliosphere talking back. The comet was less performer now than instrument, its form singing the shape of the solar wind. We are good at measuring, less good at meaning. Still, people asked, what had it brought us? What had it taught? The answers were patient and cumulative, like frost building on glass. We learned that interstellar comets are not unicorns but pilgrims, common enough that our newer eyes can catch them, varied enough to keep surprising us. We learned that chemistry rhymes across the galaxy but does not copy, that ratios of familiar gases can be skewed toward the unexpected, and that even after eons in the deep cold, ices can erupt into life at the touch of sunlight. We learned that survival near the sun is a spectrum, neither pure victory nor simple demise, but a shedding, a tempering, a change of state that writes itself in dust. But something else happened, quieter and stranger. The outbound weeks taught us how our own minds flare near the bright and ease toward the dim. When 3-Eye Atlas blazed, we projected our mythologies into its fire. Messenger, omen, probe, threat, sign. Now, as it receded, our breath returned. The fever broke, and the questions condensed into what we do best: careful looking. In the glow's retreat, wonder did not vanish. It matured. Under crystalline skies, amateurs kept their vigils. They learned the comet's temperament like a friend's, how it liked to lift from the horizon at a certain hour, how thin cloud could flatten its tail, how a window of steadier air might sharpen its edge for a handful of seconds that made a night. They posted images, arcs of light against farm silos, silver threads above city glow, a ghost crossing the spine of the Milky Way. In each frame, the comet was smaller, but in each caption, bolder. They were less about spectacle now and more about belonging. about having stood outside in the dark and witnessed a thing from beyond our scattered lights and ordinary days. In control rooms lit by console glow, astronomers stepped through data that, to most, would look like static and smears. Here, AD, line from water, faint and fading. There, a swell of carbon species slipping beneath the noise. The weird notes that had sparked wilder imaginations settled into patterns explicable by physics and sunlight. A few anomalies held out, stubborn and tantalizing, but even those began to feel less like a message from intelligence than like the signature of a nucleus that had been cooked and cracked and refrozen a dozen different ways by stars not our own. If there was intent in Three Eye Atlas, it was the intent of nature, to make and unmake, to fling and to reclaim, to write stories that are neither about us nor entirely apart from us. Days lengthened, the tail thinned to a calligraphy stroke. The ion ribbon winked in and out with the gusts of the solar wind. The coma clung tight around the core, now more grit than glow. Photometry teams chased its fading as if chasing the last note of a song. It was like watching a ship's lantern disappear into fog. You stare until your eyes invent light, until you blink and admit you've reached the limit of what the night will give. And then, because every story has a line you do not notice until you cross it, the comet slipped from the purview of the big scopes that had loved it best. It was not truly gone. It had simply moved far enough, dimmed enough, that the world's cabled nerves paid attention to nearer fires and newer flares. A few instruments kept listening, dogged and faithful, instruments with patience coded into their power budgets and pointing schedules. They eked signal from silence, wringing the last droplets of meaning from a dimming trail. If the inbound half had been a thunderclap and the sun a drum, the outbound half was the slow wave that follows the strike, rolling and rolling until it merges with the long, calm sea. And in that sea, there was a thought, hardly louder than breath. This is not an ending, only a reckoning. The comet had taken the measure of our star and been measured by us in turn. It had bound us briefly to a narrative older than language, a stone's long fall through light, a snowball's breath turned to banners, a wanderer's crossing made visible by fire. People asked what would become of it. The answer felt both intimate and vast. It would cool, the vents would seal, the ice-glass caverns would grow quiet as caves after tide. The rotation might slow or wobble and settle into some new rhythm written by the kicks and torques of its near-sun dance. The dusty skin would darken, its albedo dropping until it was once again a coal in a bottomless night. It would pass beyond the reach of household cameras, then beyond the reach of national observatories, then beyond the reach of dignified, peer-reviewed curiosity. And then it would go on, onto the dark lanes between the arms of the galaxy, on past stars whose light would touch it and not mention it to their planets, on into currents of gas that could tug at its path the way a river braids a sandbar. If it had fragments, they would stay with it a long while, like geese in V formation, drifting until some future nudge split them further or drew them together with the faintest of caresses. After a time beyond measure, some new sun might feel its passing like a tickle at the edge of a cloud. That sun's children might look up and have their own bright month of omen and conjecture. And then they would write their own reports, whisper their own metaphors, stand in their own fields and point and say, there, here, in our brief overlap with its unthinkable arc, we did what beings like us do. We listened, we measured, we argued, We stood under the same sky with strangers and felt less strange. If there is a moral, and perhaps there needn't be, it is not about danger or salvation, but about kinship with motion and change. The comet did not come for us. It came because gravity is a long, patient hand, and yet we made meaning in its wake, because that is our long patience too. In the end, after the last coordinated campaign yielded its last graph, after the final late-night press conference answered the final eager question with an honest, "We don't know yet," the comet left us a gift that will outlast the headlines. Shelves of spectra, maps of dust, time series of brightness like a cardiogram of a heart we will never hold. Models tweaked, software improved, observing networks knit tighter by the demands of a thing that does not wait. And in a million small ways, eyes recalibrated to look for the next faint visitor that will slip out of darkness and into our circle of knowing. One cold, clear morning, an amateur in the high country set up a small refractor, not to chase the comet, long gone beyond his optics, but to watch Jupiter and its moons. Old habits linger, though, so before he packed up, he panned along the ecliptic, just in case. The field drifted, stars sliding by like quiet ships, and he felt again the hush that had followed the fire. The odd tenderness one can feel for a thing made of stone and ice. He thought of the nights he'd spent with neighbors who weren't neighbors until they shared a thermos and a sky. He thought of the way the comet's tail had seemed to point at him, even when he knew it pointed away. He blinked, laughed at himself, and at last capped the lens. Out there, beyond our gossip and our bandwidth, the traveler kept going. Sunlight thinned to a veil and then to memory. The heliosphere's edge waited like the faintest seam in cloth. On the far side of that seam, the interstellar wind, colder, older, would take the dust that clung to the comet's path and comb it straight. The nucleus would carry its quiet heat for years, for centuries, and then forget, and then remember only when the next star's breath woke it again. If that day comes in a time with watchers, they will write their own Chapter 7, their own Chapter 8. They will call it by another name. They will say, "It is speaking," and then, "It is leaving," and they'll mean both at once. For us, the chapter closes as the light closes, not with a door, but with a distance. If you step outside on a cold night and listen, no sound will carry from the place it is gone. And yet, looking up, you may feel the space between stars as less emptiness than invitation. Somewhere in that invitation, a path is fading that was briefly ours to follow. We did not waste it. We learned to hear with eyes. We learned to see with questions. We learned for a season to be warmed by fire we do not own. The comet is smaller now than any word can hold. But the wake it carved through our attention remains bright, in instruments newly tuned, in friendships knitted at 3 a.m., in a sharpened sense that the universe is not a picture on the wall, but a wind you can stand in if you are willing to be changed by it. The sun is quiet again. The furnace door is shut. In the dark beyond the planets, a traveler hums its slow, outbound note. We hum it back and wait. The outbound hush did not end with silence. It resonated. Like the ring of a struck bell, the comet's passage left vibrations in the fabric of our attention, a lingering pulse that refused to fade even as the nucleus receded into invisibility. Three-Eye Atlas was no longer a spectacle for the naked eye, no longer a headline for morning papers, but it was everywhere in the quiet spaces of astronomy, in the patient work of sifting through what it had left behind. In laboratories, grains caught in aerogel collectors sat under microscopes, illuminated by beams finer than hair. These grains were so small that their shadows were larger than themselves, yet they held chemistries older than Earth. Their isotopic signatures sang of other suns, ratios not found in our neighborhood but natural in theirs. Some whispered of carbon chains so tangled that they looked almost like the precursors to biology. Others spoke of metals forged in distant furnaces, cooling at rates that told of different stellar winds, different interstellar environments. Each particle was an emissary, a fossil of a system whose light we might never see directly. But echoes are not only physical, they ripple through culture, through story, through imagination. Across the world, the comet became metaphor. Novelists spoke of it as the traveler who arrived uninvited and departed unchanged, reminding us that our dramas are small against the backdrop of eternity. Filmmakers sculpted frames of light cutting through black, of tales burning like divine brushes across the cosmos. In classrooms, teachers used it as a hook. If this snowball from another sun can reach us, what else might wander between stars? And children, wide-eyed, asked whether the comet would ever return, whether it had noticed us, whether it was lonely. In truth, the comet's loneliness was our own. It had no need for witness, no hunger for myth. But in its brief intersection with our orbit of thought, it showed us our craving for connection, to objects, to narratives, to things that remind us we are not isolated in an empty dark. Astronomers returned again and again to the same paradox. It was just a rock and ice, and it was not just a rock and ice. Both truths sat side by side, neither erasing the other. On mountaintops, telescopes continued their long integrations, pulling photons from the thinnest trickle of light. Even in fading, the comet had more to tell. The ratios of deuterium to hydrogen shifted subtly as sublimation ceased, an aftertaste of processes locked deep in its body. Its spin wobbled less, as though the violent geysers of its perihelion passage had at last spent their torque. The coma shrank to invisibility, but software teased it out in false color, mapping a ghost that clung stubbornly to the point of light at the center. The outbound phase became a study in whispers, changes of 1%, hints at the level of noise, signals rescued from the edge of absence. And somewhere in those faint data, mysteries remained unsolved. The anomalous spikes in spectral lines, were they real chemistry or tricks of scattered sunlight? The fragment glimpsed near Mars, was it a companion or a mirage? The peculiar pulse of brightness, almost like a heartbeat, was it rotational modulation or something less understood? Even in retreat, the comet kept us guessing, a magician who departs leaving one last puzzle unsolved. The public, too, carried its echo. Social feeds filled with farewells, blurry smartphone shots, telescopic marvels, poetic captions. Hashtags trailed off, replaced by the next storm, the next eclipse, the next terrestrial drama. But for those who had watched carefully, who had waited outside on cold nights, something lingered. They found themselves glancing up more often, tracing the ecliptic with their eyes, wondering what other wanderers might already be inbound, unseen, waiting to ignite their own fleeting blaze. Scientists prepared papers, thick with figures, dry in tone but carrying quiet awe. The second confirmed interstellar object observed in our solar system, they began, and the rest was analysis. But between the lines was astonishment. The fact that we could even catch such a thing, measure it, argue over it, was itself a miracle of timing and attention. In conferences, slides glowed with spectra and models, And behind the equations was a shared undercurrent. Wonder that this fragment from elsewhere had passed close enough to leave fingerprints on our instruments. As months became years, 3i Atlas dimmed beyond reach. Its echoes lived on in archives, in memory, in the recalibration of our instruments. Observing networks, tested by its brief frenzy, stayed more tightly knit. Sky surveys tuned their algorithms, more vigilant for the faint intruder that might appear tomorrow. We had been reminded that the universe is not static, that things come to us unannounced, carrying secrets from other nurseries, other times. And so, the echo became preparation. Next time, we vowed, we will be faster. Next time, we will send a craft to meet the wanderer face to face, to taste its breath, to cradle its dust before the sun remakes it. 3i Atlas had been a rehearsal as much as a revelation. The next traveler might find us not only watching, but ready to reach out. Yet for all the planning, all the science, there was still that human silence at the core of the story. The silence of looking up, seeing a ghostly tail unfurl, and feeling that strange pull in the chest. The sense of being small and vast at once. That silence, too, was part of the comet's legacy. We do not only learn by measuring, we learn by being moved, by standing still under the night sky, and letting something unearthly pass through us, even as it passes by. And so 3i Atlas continued outbound, trailing its whispers, carrying the echo of our gaze. It was gone, but it was not forgotten. For in its brief fire, it had given us what all travelers give, a story to tell when the night is long, and a reason to keep watching the horizon of the stars.